So this is lecture 52, addition of velocities. And so what we're going to talk about today is the addition of velocities. Recall that from Galileo, so I'll write Galilean, when you have an object on a moving object, the velocities add. Right? So here we have a reference frame with our observer standing on the platform. The train is rolling by with velocity v. And on top of that train is another train, also moving at velocity v prime, relative to the first train. Okay? And so the question is, what is the velocity of the second train relative to the platform observer? Do you understand the problem here? You've got a train which is rolling along the tracks, and on top of that train is another train rolling along that train, you see? So under Galileo, these velocities would add. We'll call the relative velocity of this second train with respect to the platform W, and it will be equal to V plus V prime. I can make that plus a little more plus-like. There we go. Everyone remember that? Does that make sense?
Yeah.
Yeah, okay. So the question is, what does this look like in special relativity? Well, let's first draw the reference frame of the, we're going to put ourselves on the train, first train, okay? I'm going to give these observers names. I'm going to call this observer O. I'm going to call this observer O prime. I'm going to call this observer on the second train O double prime, okay? So here we are in the reference frame of O prime. So this will be T prime and X prime. Now there should be no confusion about why the axes I've drawn are just regular old orthogonal Cartesian coordinates, right? Because since we're in O prime's rest frame, we're not moving, right? We're stationary. Yes?
Yeah.
Okay, so that's why I've drawn it this way. But in O prime's frame, the train on top of it will look like this. It's going to have a whirl line, which we'll call T double prime. And of course its X double prime axis will be symmetrical about the light line, which I did not draw, but I'll draw it. X double prime, right? And so we can use what we know about Lorentz transformations directly here, right? So what we can write is that X double prime, right? That's the position on the second train, right? In the O prime prime reference frame, will be equal to a gamma. But I'm going to note that the relative velocity in this gamma is v prime. So I put the v prime in the gamma because that's the relative velocity of the second train to the first train. You understand?
Yeah.
So if I'm on this train, the second train, that's how fast it's moving, v prime. Okay? The reason I'm putting it there is because we're going to later use another expression which will depend on this relative velocity of the train to the platform. Just want to let you know why it's there. Normally we just write gamma, right? Because we only have one relative velocity we're worried about. And it looks just like we normally write it, right? We're going to write x prime minus v prime, because that's the relative velocity, t prime. Okay? Does that look familiar if you think about it? If I have a measurement in the train's frame, right? That's the O prime reference frame. It will have measurements of x prime and t prime, right?
Yeah.
And I want to know what is the x prime value. What is that spatial value on the second train, right? Because its rulers are moving, yes? So that's what this is, x double prime, okay? And so it's totally analogous to the systems that we've been considering where the platform, right, is compared with the train. And we say, well, the coordinates in the train are equal to the coordinates on the platform under this transformation, right?
Yeah.
Okay. So totally analogous to that. We also have the t double prime will be equal to gamma v prime times t prime minus v prime x prime. Also analogous to what we did for a train and a platform. All right, so that's for that coordinate system. But what about the platform? Well, we can draw the platform coordinate system where this will be the t-axis and this will be the x-axis. This is what we're used to, right? And of course, there's our light line. And this time, that's a terrible whirl line. This time, this is the t prime axis. You see that? And this is the x prime axis. So in the platform frame, this is what the O prime frame looks like, right? T prime, x prime, right?
Yeah.
Okay. And so here I can write the Lorentz transformations, which we're kind of familiar with, right? This will say that x prime right, is equal to gamma, and this time the relative velocity is just v, not v prime, v times x minus v t. And t prime will be equal to gamma v t minus vx. Right? We should be familiar with that. Yes?
Yes.
Okay. So I don't actually need the space-time diagrams, but I do need the room here to show what we're going to do next. So what we're going to do is we're going to substitute, I'll call this 2, since it's the second thing we came up with, and this 1. Our strategy is going to be to substitute everything in 2 into the first equation in 1 up here. So let me just rewrite the first equation. X double prime is equal to gamma v prime times x prime minus v prime t prime, right? So x double prime equals gamma v prime times the quantity, and I'm going to substitute x prime in from here. That'll be gamma v times the quantity x minus vt, right? Minus v prime times t prime. The t prime I'm going to pull in from here. See it?
Yeah.
So t prime is gamma v times the quantity t minus vx. Okay? See what I've done?
Yes.
Now I'm just going to change it up just a little bit. Okay? I'm not going to do a lot of manipulation here, but I am going to rewrite this as gamma v prime times gamma v times x minus vt minus gamma v prime. I'm just distributing the gamma v prime. That's really all I'm going to do. Times v prime t minus vx. Okay? Just distributed the gamma v prime into both of these terms. When x prime is equal to 0, so if x prime is equal to 0, where's x prime? Here's x prime. If x prime is equal to 0, what does that say? So I'll let x prime be 0. So that says that gamma v prime, just gamma v, times x minus vt, right? I can get rid of the gamma, right? Because I can divide that into the 0, right? And then I'm just left with 0 equals x minus vt, which says that x is equal to v times t, right?
Yes.
Now why am I doing that? Well, because I want to get a relative velocity out of this, okay? This is the relative velocity v. I got it from here, okay?
Okay.
So what I want to do now is I want to let x double prime be equal to 0. So I'll let x double prime equal 0, right?
Yeah.
If I do that, that means I have 0 equals all of this stuff, okay? You can see I can divide out the gamma v and gamma v prime, right? So all of that will go away and divide it into the 0, and I'm just going to be left with x minus vt equals v prime times t minus vx. Do you see that? If you don't, work it on your whiteboards. This is just going to say 0 equals the quantity x minus vt minus v prime times t minus vx, right? So I can just move this 0 here and make this equals, right? So those are equal to each other, okay? I want to distribute the v prime, so this will be v prime t minus v prime times v times x, all right? I'm going to get rid of the parentheses. Now I'm going to collect like terms. I've got an x over here and an x over here. I've got a t here and a t here. I want to move those together algebraically. All right, so this is going to give me x plus v prime x equals, I'm going to move this t over here. So that'll give me v prime t plus vt. Yeah?
Yeah.
It's just algebra.
Yeah.
I'm going to factor out x. So that gives me x times 1 plus v times v prime equals, factor out t over here, t times v prime plus v. Okay?
Okay.
Everyone see that?
Yeah.
Now, look at the form of this guy. The x equals something times t, right? So all I have to do is divide out this last term here, right? And I'll put it under here. I'm going to put the t back here so we can see it. I'm going to move this under here. That's 1 plus v prime. Now, I guess I don't need the parentheses, so I'll just get rid of those. Here we go. The x right there. So now I have x equals some quantity times t, right? As a result of having let x double prime equal 0, right? And if I look at the form I had up here, that v, this is the relative velocity v, this is the relative velocity for the second train with respect to the platform. Okay? So now we can write, well, I guess we'll write Einstein, and I can get rid of this. W equals v prime plus v divided by 1 plus v prime. So it looks almost the same. I guess I can move the v prime over there, right? It looks almost the same as the Galilean transformation, except we're dividing by this term here. 1 plus the product of the two velocities, relative velocities. You see that?
Yes.
So what are the consequences of that? Don't need this. Let's just get rid of it. What if we let v equal v prime equal 0.99 c? It's 99% the speed of light. Well, under Galilean relativity, right, we would get that W equals 0.99 plus 0.99, which is 1.98 times c. So almost twice the speed of light, right?
Yeah.
Which is what you'd expect for a baseball if you were throwing a baseball on a train, or if you were riding a go-kart on a train, right? You expect the velocities to add, right?
Yeah.
So that's what we get for that. What about special relativity? What do we get? Well, we're going to get the same term in the numerator, right? Because it's just the sum of the two velocities. So that'll be 1.98 divided by 1 plus the product of the two. And if you multiply this out and add it, you'll find this is equal to 1.9801. If I divide this into this, I'm going to get 0.99995. Okay?
Okay.
So the question is, can this ever be greater than 1, greater than the speed of light? Right? Can W be greater than or equal to 1? Remember, speed of light we're calling 1 because we normalize the speed of light c to 1. So no speed less than the speed of light will be bigger than 1. That's a weird way to say it, I agree. But can the relative velocity of something be greater than the speed of light? That's the question.
No.
Well, that's the correct answer, but let's prove it, okay? So how would we prove that? Well, remember what our formula says. So if W is greater than or equal to 1, what does that mean? That means that, let me write it. I need a little more room. So I'm going to write it right over here. W greater than or equal, really, I want to prove that it's less than 1. So I'm going to write it like this. W is less than 1, okay? All right, so if W is less than 1, that means that V plus V prime divided by 1 plus V prime is less than 1. But I can move the 1 plus V prime over here, provided that V and V prime are both positive numbers. And I'm just going to rearrange it a little bit and write it this way. 1 plus V times V prime is greater than V plus V prime. And so that is what we need to show. Okay? And here's how we're going to do it. Here's the trick we're going to use. We're going to write 1 minus V times 1 minus V prime is greater than 0. It's not an unreasonable assumption. Okay? V and V prime I'm going to consider are both between 0 and 1. If V and V prime are less than 1. Less than 1. Okay? If V is equal to 1, or V prime is equal to 1, we get a 0. 0 is not greater than 0. So it's got to be less than 1. Okay? Now, this is your job. Multiply these two out for me, please. 1 minus V times 1 minus V prime. What did you get?
1 minus V prime minus V plus V times V prime.
Okay, so now we've multiplied that out, right? Let's move the stuff with negative signs on them over to the right, okay? And that gives me 1 plus V prime is greater than V plus V prime. Look familiar? What were we supposed to show? We wanted to show that 1 plus V times V prime is greater than V plus V prime, right?
Yes. Yeah.
What did we demonstrate here?
That 1 plus V times V prime is greater than V plus V prime.
Yeah, we showed that. So that, we can write QED, like the mathematicians like to do, right? This box is the same as this box. We have shown what it was we needed to show using this, okay?
Okay.
It's an interesting proof because there's a trick that you can employ here. If I were to consider more than just two terms, let's say I put another train on here. We'll call that O double or triple prime. Right? We'll give him a relative velocity with respect to the second train of V double prime. Right? See that?
Yeah.
So, if I were to move that out of the way, I'm going to add one more term to this, 1 minus V double prime. Okay? Now, if I do that, it's actually quite a bit of algebra. But what we'll see is we'll have a bunch of stuff with some negative terms in it. Let me just write it. If we multiply that out, we'll get, right, this is greater than 0. Right? If I then move all of these terms over to the other side of this inequality, right, is greater than double prime. And analogous to what we had done before, right, this part here constitutes the denominator of our relative velocity of that third train. So 1 plus V prime plus V double prime plus V prime V double prime. And this part constitutes the numerator of that relative velocity. So you get V double prime plus V prime plus V plus V prime V double prime. So, and you can confirm this, it's not fun to do, it involves a double substitution. You do it exactly as we did it before, except you'd add an additional reference frame that you started with, and you would substitute from the second one into the third, and then from the first one into the second, right? And it's a bit messy, but you will confirm that this is exactly what you get, and this seems to work for any number of trains on trains on trains on trains. And the velocity will always be, the relative velocity will always be less than 1, or less than the speed of light, okay?
Okay.
It's unusual because it doesn't look exactly like what we started with. It does have the sum of the three velocities, sum of the three relative velocities, but it also has this mixed term at the end here, right? Plus the product of those three. And we're dividing, but we are dividing by all the possible combinations of velocities, right? So it's V with V prime, V with V double prime, V prime with V double prime, and those are the only ones you get, right? I think, how many different ways can I combine these three relative velocities? Right, we've got 3 ways. V prime, V double prime, V prime, V double prime. Okay? So it takes the same form. I think I looked at it for, I think, one more car on top, and it gets a little bit weirder, but yeah. That's a kind of a shortcut or a trick that you can use to calculate the relative velocity of a whole cascade of items, right, that are on top of each other, right? So it's the speed of the go-kart that's on the train, that's on the spaceship, that's orbiting the planet. And you can get the speed of that go-kart relative to the planet. You see?
Yeah.
Provided it's moving over a linear swath of space. But now, of course, there's another way you can deal with the addition of velocities for a large number of velocities that you need to add up, and that's using hyperbolic coordinates, in which case it's linear. But hyperbolic coordinates is well beyond the reach of an introductory level class that depends only on algebra. So, all right, that's all I have to say about the addition of velocities. Notice the distinction, the difference between Galilean and special relativity's version of the addition of velocities. It's mostly, at least for 2, it's this right here. You've got this denominator, which keeps it from ever getting bigger than 1. Okay?
Okay.
As a result, nothing can go faster than the speed of light. Okay?
All right.
That's it.